Today we are gonna be solving a monster from 2023 Berkeley integration bee, which is the integral from 0 to 2 of x multiplied by the square root of x to the power of natural log of x multiplied by the cube root that's under that first square root of x to the power of natural log squared of x multiplied by the root 4 of x to the power of natural log cubed of x, and so on. You probably see the pattern already. So how are we supposed to solve this guy? Well, first of all, let's try and clean up those exponents for a little bit. I don't really like, those infinitely long roots there. I'd like to make it a little bit more rational. You get the joke, I hope. Yeah, so I'd like to make all of the powers here in this integral just, be rational powers. So let me do it. What I'm gonna, how I'm gonna write this integral is, first of all, I'm gonna just, I'm gonna make my rubber a little bit more smaller. Yes, I'm gonna write it as the integral from 0 to 2 of x to the power of 1, the first x, the guy right over there, multiplied by x to the power of natural log of x all over 2, that's this guy here. He's under the square root, so he's dividing this, so I'm dividing this natural log by a 2. There's gonna be x to the power of natural log squared of x all over 2 multiplied by a 3, yeah? So 2 times a 3, that's this guy over here. He's under a cube root and also under a square root, and then multiplied by x to the power of natural log cubed of x of 2 times 3 times a 4. I'm just gonna be extending this guy into infinity. But now I don't really like the idea of multiplying infinitely many x's together. I would like to squish them into a single x and then just raise that x and, well, infinitely long power. Yeah, let's just do it, yeah? It's an awesome idea. So what I'm gonna get is the integral between 0 and a 2 of x to the power of 1 plus natural log of x all over 2 plus the natural log squared of x all over 2 times 3, and so on and so forth. I'm not going to be extending it any further because this this exponent is already too long for the base. So just going to call it a day and write a dx over here. Okay, but how can I rewrite this exponent? So it's a little bit shorter, let's say. Well, this thing is actually a pretty lovely looking sum. Actually, can I write it as the integral between 0, oh, that's an awfully looking integral, and now it's a little bit better, from 0 to 2 of x to the power of the sum as n goes from 1 up to infinity of the natural log of x to the power of n minus 1 all over n factorial. Because you see, those those degrees of roots are going to be multiplied by they're going to be multiplied together and they will just form, this n factorial here in the denominator. That's all going to be dx. But now, well, what is this stuff here similar to? I mean, if there's one sequence, one series, one sum that you should remember from Calc 2, it is the Taylor series expansion for e to the power of x. It looks something like this. It was e to the power of x being equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on up to infinity. That's actually rewritable as the infinite sum as n goes from 0 to infinity of x to the power of n all over n factorial, and those two sums are actually pretty similar to each other. I mean, there are slight differences. I mean, we are raising this ln of x to the negative first power. This n is risen to the nth power there. We are starting with n equal to 0 in the Taylor series expression for e to the x, and we're starting with n equal to 1 in our integral. But it's, still something, because I'm thinking maybe we'll be able to get this guy to a form like the sum as n goes from 0 to infinity of the natural log of x to the power of n all over n factorial, because this thing is actually equal to e to the power of the natural log of x. Well, this thing is just x, so this is a lay that I would really like to work out here. I'm just gonna put this guy in pink right over here so it kind of reminds us of where we are going, and let's right now try and do something about those logs. So first of all, well, the first problem here in the integral, the sum starts with n equal to 1 and here with n equal to 0. There's no problem in that. We can just take out the first term from the Taylor series expansion for e to the x. We're going to get 1 plus the sum as n now goes from 1 up to infinity of x to the power of n all over n factorial. But now we've got an n plus 1 in the exponent here in the sequence in the integral, but we've got an n, a whole n, without that n minus 1 in the Taylor series expansion for e to the power of x. There's no problem in, well, any of that, because we can just rewrite this integral we've got right over there as the integral from 0 to 2 of x to the power of 1 over the natural log of x, 1 over the natural log of x, multiplied by the sum as n goes from 1 up to infinity of the natural log of x to the power of n all over n factorial. But now, well, what is this guy here? Well, as I've just showed you here, we know that this guy is equal to e to the power of x, and so this guy, the sum from 1 up to infinity of x to the n over n factorial, is equal to e to the x minus 1. And now just plug x equal to natural log of x, and you will get pretty neatly the sum as n goes from 1 up to infinity of the natural log of x to the power of n all over n factorial is equal to e to the natural log of x, which is just x, so x minus a 1. But well, this stuff right here is exactly what we've got there, and so we can just plug it into our integral. I forgot the dx here, and rewrite this integral as the integral from 0 to 2 of x to the power of 1 over the natural log of x multiplied, and now plug x minus 1 for this sum here. We're gonna get 1 over natural log of x times x minus a 1 dx. But what are we supposed to do with this guy now? Well, just recall that there is no problem for us to say that x is equal to e to the power of natural log of x. And why would I want to plug in x equal to e to the natural log of x into the integral? It will simplify things quite nicely, because it will give us the integral from 0 to 2 of e to the power of natural log of x to the power of 1 over the natural log of x multiplied by x minus 1. So those two things, those two natural logs, the reciprocal of it and the natural log of itself, are going to cancel each other out. And what we will be left with is just the plain old integral between, once again, 0 and 2 of e to the power of x minus 1 dx. But there is no problem in just saying that this thing will be equal to e to the power of x minus 1 between 0 and 2, which is e minus the reciprocal of e. And this is the final answer. So let's once again go over what we did here in this problem. So first of all, we cleaned up the exponents in the infinite cave of those natural logs. It turned out that there's a pretty nice representation in terms of exponential function of the sum, of this infinite sum of natural log in the exponent of x. We used that thing and got that this integral was actually equal to the integral between 0 and 2 of e to the power of x minus 1, which was just e minus 1 over e. I hope you guys enjoyed it, and see you in the next one. Bye.